So you probably heard a lot about it. There's a lot of hype and this and that surrounding neural networks, and a lot of the excitement in machine learning has been surrounding neural networks. They're not new; they've been around for a while, but it's only recently that we've had enough data and computing power to take full advantage of it, or make better use of it. Not to mention, there's been some optimizations done here and there. So this week, we'll be talking about a few things. So the perceptron, which is the basic, unit within your neural network. You can think of it as a neuron, using the brain analogy. We'll talk about how the perceptron learns, using either the perceptron learning rule or gradient descent. And then after we've talked about each individual piece of the neural network, we'll talk about the actual neural network, and then how that learns using backpropagation. And then we'll talk a bit about convolutional neural networks. And of course, we also have our lab today. And the lab essentially builds up a perceptron. And then after that, do we get a network going? Yeah, it essentially builds up a perceptron from scratch. And you learn, or you use a perceptron learning rule or gradient descent to fit your perceptron to the data. So those are the two things that we want to talk about today. All right. So hopefully you can see this. All let me know if it's a bit small. I'll try to zoom in, but assuming my internet connection is not this again. Assuming my internet connection is fast enough, then it shouldn't be a problem. I just left this to the right. There we go. Make that a bit smaller, a bit bigger. Cool. Bit of introduction. I think I spoke about these a bit already. The neural networks, a lot of exciting stuff. It's fantastic. We're finding it's really good for computer vision, natural language processing. Those are things that historically we've had a lot of difficulty with. So I don't know if you recall the old days of facial recognition or computer vision. It really wasn't very good. It didn't perform very well. And you might remember back in the day, Google Translate was a bit of a joke, but now both those things are quite good. And neural networks have been the driving force behind a lot of that. And of course, you guys might have heard of AlphaGo. There's a whole bunch of things behind that, but they got neural networks involved in that as well. Cool. So let's talk about the brain analogy. So why is it called a neural network? Well, they approach. So many years ago, scientists were looking at the human brain, looking at for inspiration in terms of building these models. And your brain is made up of, I don't know if I have the right order, if it's millions or billions, but there's a lot of neurons in there, and a lot of them all wired to each other, and electrical impulses. You have you can see here, you'll have a neuron here, and it'll be connected to a whole bunch of other neurons, right? And then electrical impulses will go from all those other neurons to this neuron. Again, I'm not a doctor, I'm not a biologist, so I'm probably bastardizing a lot of the terminology, but I'm just going to call this a neuron. If enough of an impulse goes through, then this will activate and then fire another electrical impulse to whoever it's connected to, the other neurons it's connected to. So that's essentially the inspiration of, the neural network. So this is if you look here, so here's our neuron here, and then here are wirings from other neurons, if we're using the brain analogy. So that could be, in this case, there's say 4 or more than 4 neurons, and they're all hooked up to this neuron, and then it'll fire off, and then it may stimulate some more neurons, right? So this looks a bit complicated, but really, it should be a little familiar. Again, I'll move to the next slide, and you'll kind of see why. But essentially, if you break it down, there's a couple of different parts to this. There's what's called the input layer, right? And it takes in a bunch of x values. So you can kind of think of these as, the features or the predictors within for this particular neuron, and then there's a weight attached to it, right? So what will happen is these inputs, they could be a variety of things. Perhaps in computer vision, each one of these could represent a pixel, right? Or if you're doing, some sort of regression task, say house prices, this could be, I don't know, this could be square footage or meterage. So the area of the house. This could be, I don't know, some proximity measure to the coast. This could be the number of bathrooms, etc., etc. So you can kind of think of these inputs like the features, right? And then you take the sum product of all this, or you can think of it as the dot product between the x vector and the w weight vector, right? So that all goes through, and then there's something called an activation function, which I'll talk about in a bit, and then there's an output. But if I go to the next slide, you can see how this whole concept of the basic perceptron should be a little familiar. You might recall the basic linear classifier that we've been talking about over the past however many weeks. It was the basic linear classifier was it was a straight line or a hyperplane, right? And if you look here, right, this is our basic linear classifier. Anything that sits above the line, we'll predict as positive class. Anything that sits below the line would predict as a negative class, right? So, but really, what was that? You could have expressed that hyperplane as something like this, right? Actually, sorry, maybe I shouldn't call this y. This would be what notation? Maybe capital sigma. Something. I think that's what they used here. Yeah. Okay. Cool. So we'll call this. So this should look familiar. This is the same form that the basic linear classifiers that we've been seeing before are, and this is, a hyperplane, an equation of a hyperplane, or a straight line if it's only in 2 dimensions. And you might recall our classification or prediction rule was quite simple. It was just that if the sum product of this guy here, which is your weights and your predictors, if it was greater than 0, geometrically speaking, if this was positive, it means it lies above this line. We'll call it the positive class. And then our prediction rule, if this was negative, it would geometrically mean that it would sit below here, and then we'll call it the negative class, right? Now, of course, we can actually code that up into what's called the activation function, right? So this part here was the input from our basic linear classifier. That's essentially this guy here. And see this capital sigma here? That is a sum product, which is here, right? And to convert this into a decision rule, this is essentially our, and then I guess we put sigma into our activation function, which was something like this, if, so I should call that. If the sum product was greater than 0, then we'll call it, our prediction would be that it's positive. I'll just go else would say our prediction is of the negative class. I'll say -1 here, right? Sorry, not -11, -1. Cool. So this is our binary step function, and you can kind of see it a little bit here. Just put that over here. You can kind of see it a little bit here. So we take our sum product, which will denote capital sigma, and then we feed it into something to have, I guess, our decision rule, right? And our decision rule was essentially, if this was positive, we'll call it 1. Otherwise it's -1. That's essentially this binary step function here. Now, if you look up activation functions, there's a whole bunch, and don't worry if this whole activation function concept sounds a bit confusing to you. I'll talk about it in a bit more detail later. But this function is essentially the binary step function, although it's been shifted, I guess, down to -1 and 1. But it's basically something like this. I don't know if there's another name for it, but I couldn't find something closer. And I think in the lecture notes they're calling it some sort of step function anyway. So I'm just going to call this a step function, right? And you can see why. So if if the input is less than this guy here, this function is essentially this rule here, which I'll call the step function, our step function, right? So hopefully you can see how the perceptron is a basic linear classifier, and hopefully this is jogging your memory a little bit as to where this all came from. Cool. So that's a perceptron. So just this whole concept here, that this is just but one neuron. So in a neural network, which we'll talk about later, you're going to have many of these, right? And each one will be hooked up to a bunch of neurons from the previous layer, which in turn will be hooked up to a bunch of neurons in the previous layer. But if you just take one neuron or one perceptron, you can use it as a basic linear classifier, of course, with the appropriate activation function, right? So just a bit of terminology. Sorry. So this here is called, let me just move this guy down here a bit. So this here is called the input layer, and this guy here, this guy here is called the activation function. Sorry, it's a bit, I'm gonna call it this activation function. Sorry, I know it's a bit hard to read, but you get the idea. And then this final bit here is called the output layer, and it should be reasonably obvious why this is called the input layer, just what goes into the perceptron, and it should be reasonably obvious why this is called the output layer. It's what comes up. And in this case, with something very simple, a basic linear classifier, the input layer here is just say your features. If we're going to use, say, that fish classification example, maybe positive is salmon and the negative is sea bass, then the input layer would be the features, say, I don't know, say the height, the length, dorsal length or something, and the weight of the fish. I don't know anything about fish, but that would be what goes into the input layer. They'll all be given some sort of weight, and it turns out to be a straight line. And then the activation function was essentially our decision rule. I need a better way to do these arrows, don't I? Looks a bit funny like this. Yeah. Okay. So, yeah. Maybe I'll make that a bit smaller. There we go. This is the same as our perceptron. Now, with our basic linear classifier, our input layer was just the features going in, e.g., I don't know, say fish length, fish weight. Okay, and an activation function was just our prediction rule, as above. So this prediction rule here, and an output layer was just our prediction, so positive or negative class. In this case, salmon or sea bass, for example. Cool. So hopefully that gives you a bit of an understanding or flavor as to the perceptron, our basic unit within the neural networks. Let me make this a little bigger. Right. So this is all well and good. But then the question may be, okay, how do we fit this line? Now, throughout this course, we've actually seen a bunch of different ways to fit a line. You might recall with our support vector machines, if you had this kind of a problem with our support vector machines, we would essentially maximize the margin. Now, if you recall, the margin, so if I look at SVM margin, the margin was the distance from the separating hyperplane to the closest point from each class on each side. So you can think of it as, I like to think of it as a road, you know, with a support vector machine, a road in the middle of the two classes, and you want to maximize the margin or the width of the road. Right, here we go. So you can kind of see a little bit here, the support vector machine. Here we go. We'll just ignore this one here. I mean, that's using a kernel, but just look at this, right? There's a road in the middle and a margin. That's how the support vector machines do it, right? You can also think of it, this isn't really a linear regression. This isn't really a logistic regression kind of problem, but you could also consider this problem as minimizing the sum square errors, you know, between, oh, actually, sorry, I take that back because it's positive negative class. You wouldn't really be using sum square errors here. But you could also look at this in terms of a logistic regression framework. But then it comes out as probabilities, and it's not really like a dividing line in between them. Yet you have probabilities. But there's a few different ways to look at this problem. I think that the closest one to this one that we've seen so far is a support vector machine. Cool. But in terms of Perceptron, we actually try to find this line another way. You know, instead of using the maximum margin, or you know, to maximize the size of the road, there's a few ways with the Perceptron, and the first one is called the Perceptron learning rule. Now, I'll go through this step by step in a bit, and then we'll look at the Jupyter Notebook, which has this is pseudocode, right? But the Jupyter Notebook is, well, it's Python code, it's real code. So in a nutshell, the way the Perceptron learning rule works is it goes through each of the observations, and every time there's a misclassification, it bumps the weights when there's a misclassification, right? So it might start with, I wonder if I can find a good picture actually, Perceptron learning rule. I probably can. And if not, the Jupyter Notebook has a bunch. Maybe I'll just jump to the Jupyter Notebook for a little bit. Okay. So we'll go through this in a bit, but this is an implementation of the Perceptron learning rule. Let me just make this a bit bigger so you guys can see. I realized later while I was looking at the YouTube video that it's a bit hard to see sometimes. Although, you know, assuming your connection's fast enough, you can zoom in. So just a reminder to everyone, if it's a bit small in Microsoft Teams, what you can do is you can hit either Control or Command, depending on your operating system, and then you scroll, and you can zoom in and out of the video, right? So that's something else you can do. Otherwise, if your internet connection isn't fast enough, later on this will be on YouTube. And then you can watch it in 1080p and just let it buffer, let the video load. Cool. Here we go. But here's the Perceptron learning rule in action. So this problem here is something similar to this problem that we have here, right? And the question was, this is great, but how do we know where that line sits? How do we know where to put this line? You could put it you could put a whole variety of different ways, right? Now, the way the Perceptron learning rule works is you initialize the weights to something random, and let's say this is something random, it's got a line here. You can see here that it's not perfect, it's not great. You can see that, okay, for these guys down here, it seems to have, assuming everything predicted down here is red, it seems to be correct. For these guys up here, it's also correct. But there's 1, 2, 3, 4. There's 4 or maybe 5. It's hard to say. Maybe 4 observations which are incorrectly classified. So what the Perceptron learning rule does is it will go through each data point, go through the data set one by one, and every time there's a misclassification, it'll bump the weights. It'll nudge the weights a little bit, right? So you can see here, okay, there's a misclassification. I don't know which one it's staring at. It might be one of these ones. I don't know. It could be this one, this one, this one, or that one. But it says, okay, let's bump the weight. Boom. Okay. So it moves a bit better and a bit. So it moves a bit closer to the truth, I'd say. And now there's only 3 misclassifications. But now they're like, okay, there's still some misclassification. Let's bump it further. And it bumps it again. this time it wasn't enough, and it keeps bumping and bumping and bumping it until here. We have perfect separation. Now I'm going to preface this and say that this basic perceptron, used for classification, it only works for perfectly linearly separable data. And I think I threw that term around a bit when we talk about support vector machines, but perfectly linearly separable data just means that, well, something like this, something like what you can see in this data set here, where if you draw a straight line or hyperplane in more than 2 dimensions, you can perfectly separate your classes. So in this case, it's perfectly linearly separable. Now, if I had a blue dot here, then it would not be perfectly linearly separable. Right. So let's go back to the pseudocode before I jump back to the real Python code. Okay. Okay. So so D is our data set. Our first step is we initialize the weight. So the W is the weight vector. So the W is so this is our W, and again, the lecture notes have grabbed things from a variety of sources, so the notation changes a bit here and there. At least when I do it, I'm going to try to stick to M being the number of observations, and N being number of features. Okay. Here's our weight vector. We initialize it here. They initialize to 0, but in practice, you'll find that they're typically implemented to some small but random number. They find that better for optimization. You chuck it into 0, often it'll get stuck, and sometimes you do need a few random restarts to help things converge and move along. But at least for simplicity, we'll set it to 0. Again, in practice, it will be something small and random, which is actually also what they do in the lab as well, which we'll see shortly. Okay, cool. So what exactly is happening here? Here's our decision rule. Here's our sine function. So this guy here, this sine function, is this guy here. So if I take a screen, oh no, I can't, can I? Because maybe I'll use the Windows one. Snipping tool. Ah, shoot, that doesn't work. Right, maybe I won't do it that way. Alright, well look, anyways, I want to take a screenshot, but I'm recording the screen right now. Did that stop? No, I think it's still recording. I hope it's still recording. Which screen is it recording right now? Sorry, let me just check momentarily. Okay, no, it's still recording the screen. It's just a little confusing when it goes to full screen. I think things are okay. It's still recording. Sorry about that. Let me reset my setup. It's just not playing nice today, is it? Alright, maybe I'll do it here. Can I? Well, I don't have that, do I? It's a shortcut to get out of here. I need to get that one. Sorry about that. Let me just try and get out of full screen mode. It's a shortcut. Command Control F. Command Control F. Why isn't this working? There we go. Sorry about that. My Mac's a bit confused, so I've got too many things going on. Windows and Mac. Alright, sorry. So what I was trying to show you was that this activation function, this sine function here, is this guy, and this is our prediction rule. So this w.x w and then bullet x. Okay, I'm gonna use boldface to indicate a vector, because it's too much of a hassle to have to make it look like a vector each time. Why is this going to be like? There we go. Okay, so this was our activation from before. I'm not sure what notation that was used, but I'm just going to use a capital sigma to denote the sum product of the weight and vector. So that goes in there. That's an activation function, and it's a sign function, and it'll be positive or negative class depending on whether the activation or this summation is positive or negative. Okay, so we set it up, and what happens is we step through the data. We go through observation by observation. Now, this if statement here is testing to see if our classification is incorrect, if it's misclassified. Now, why is that the case? If, let's say, for example, in our training data, the response, the target, is positive. Now, if it were misclassified, our w.x would be negative, based on our decision rule. So positive times negative, that's going to be negative, right? Now, conversely, if our target were negative and it were misclassified, this would be positive, and this would again be negative. So hopefully you can understand how either way, if there's a misclassification, it's going to be negative. Good. So if there's a misclassification, then what we want to do is we want to bump the weights, right? That we have a weight vector and we reassign it, and then we have the weight vector and we bump it up by this guy here. So the bump is the eta yi xi. Now let's break this down a bit to understand why we do this. So the bump is eta y and then I guess x. I'm gonna drop the index for the I guess the position and the data with the I, because I'm being a bit lazy. But this is our bump. Our bump is this guy. Now let's break this down, understand why there's this bump. Now, I'm just gonna make a bit of room. Okay, so our eta, this is our learning rate. This is how quickly the algorithm learns, or I guess adapts to the data. Now the thing about this is you have to be careful, because there's a couple of things. So if it's too low, then what will happen is it might take ages to converge, or might even never converge, right? And if you're dealing with a really big data set, especially in practice, this may be a huge issue. Now, the flip side is if it's too high, then you may miss a global optimum. You might miss, if you can imagine you're trying to descend down a hill, you're taking steps that are too big. You might step over what could actually have been a global minimum there, assuming you're trying to minimize something. And our y, well, this is just our target. Our y is just our target, and our x is the features. So what happens is if we were misclassified and the y is positive, what does that mean? It means that our sigma is too low, right? So let me spell it out. So let's say if y is actually, so let's say it's misclassified. Right, this is really small, isn't it? It's hard to see. Let me just shrink that. Let me get rid of this. I don't think that's too important. Make it a bit easier for you guys to see. That's better, isn't it? Okay. Okay, so if y is actually positive, what that means is, it means that our sigma was too small, isn't it? Because if y was positive, we actually wanted sigma to be positive as well. Now the fact that it was misclassified is telling me that this is negative. It's too small. So we actually want to increase our weights. Now the flip side is if y, so I'm assuming here it's both misclassified. Now the flip side here is if the target was -1, that means y is too big. So we want to decrease our weights. And you'll see that happens automatically here because you're reassigning it, I guess, you're reshuffling all the x's, right? But if it's too big, I mean, sorry, if y was positive and it's too small, then this will be positive. Then you end up increasing the weights. Now, if y was negative, then this will be negative and end up decreasing the weights, which is exactly what this does. Okay, so hopefully you understand what's going on. We set the weights to 0. We step through all our data, and every time there's a misclassification here, we bump up or down the weights. We bump up the weights if y was too small. Sorry, if sigma was too small, e.g. it was positive, but we classified it as negative, and we do the opposite. If y is negative. This assignment of converged to false. So what does converge mean? In this case, a convergence means that we step through the data, we go through another data, we step through the data again, and there's no change, right? We're perfectly classified everything. So we can see in this example here, right? This hasn't converged yet because there's a few errors. This hasn't converged yet because there's 3 points misclassified still. This also hasn't converged yet because there's a point there which is misclassified. Here, that's converged. That's what we mean by convergence here, and that's what that's what this converged variable is doing. It's recording if there was a change to the weight. Because if there's a change to the weights once you've stepped through the whole data set, it means it hasn't converged. Okay. So hopefully that gives you a bit of a flavor as to the Perceptron learning rule. Now I'm going to jump over to the Jupyter notebook now, which demonstrates this with real code. Now that we have a basic understanding of the Perceptron. Right. Now just a reminder, this Jupyter notebook is sitting in the Microsoft Teams file sharing facility. You don't have to worry about the helper functions. Is just generating random data. Okay. Maybe I'll put it side by side so we can compare the pseudo code with the real code. Okay, so train Perceptron. What is happening here? We are initializing our weight vector to something random, and as I say, I know this says 0 here, but random is better in practice. This is just the number of rows, number of observations / number of rows. And what happens here is we're stepping through the data one by one. And okay, so what is going on here? Let me just zoom out a little because it's a bit hard to. Okay. So this if statement here is the same as this if statement here. Yeah. So just a reminder, this @ sign is the dot product. So this is the target, and this is the prediction. So. Sorry, I'm using Windows keyboard shortcuts, but on a Mac, is y hat. It's our prediction. Now, why is this a prediction? So this is our weight vector, and this is our x. So these are our features. So you might recall the dot product. Well, it's essentially this, isn't it? So it's our weight vector dot all our features. It's a sum product of all our weights and features. And the sign of that is our prediction. Well, I mean, sorry, it's not our prediction, but I guess the sign of this is y hat, which is our prediction. So this has a domain. It could be, you know, all real numbers, a plus minus infinity. But if it's positive, you know, we'll chuck into the sign function and call it the positive class. If it's negative, we'll call it negative, and that's our prediction. Cool. So this is the same thing. Now this will only trigger. This will only be true if the prediction is wrong. So similar to here. And if it's wrong, what we do is we increment our weight vector. We're doing this here. This line here, line 7 here, is this line. So we increment it by eta times, you know, and then this will tell us whether to increase or decrease the weight. So if it was positive class and we misclassified it negative, this will be positive, and then we bump up our weights a little, right? Cool. And this is just to help our understanding. This plot scatter helper function just generates this guy here, and then generates this guy here. It just shows each step, right? Okay, right. So this steps through. These are just plots. The meat of the algorithm really sits here. So this pseudocode is equivalent to this code here. So you step through the data, and then you bump and nudge the weights until everything looks good, until everything's perfect, like in here, in this graph here. And where's the flag? Where do we break? There should be a break, shouldn't there? Or just one step through. Plot scatter. Number of iterations. So then you counter. Okay, yeah, here's the break, yeah. Because I was looking at this looks like an infinite loop. Okay, so this is to break out of the while loop by returning the function. So this is where we end. And this happens when, just going through all the data, isn't it? Yeah, so this is just one step through the entire data set. This isn't entirely like this algorithm. This algorithm ensures convergence. This, just reading this code, it just steps through the all the data, you know, one by one, and then it breaks out when when we've gone through all the data. Oh, hold on. Oh no, sorry, I take that back. They reset the counter here. So they reset the data set counter. Okay, so this will only happen if you've stepped through the entire data set, and let me just move it up here, and you haven't altered the weights, e.g. you've converged. Okay, so it is the same as this. They're done in a slightly different way, but it's effectively the same. Okay, so that's our perceptron learning rule. It might seem a bit blunt, and it is a little bit, but it does work. The key thing to remember about the linear the perceptron learning rule is that it only works for perfectly linearly separable data. I hope you can imagine. So let me pull up a data set that isn't perfectly linearly separable. I'll go soft margin SVM. There we go. Imagine you have this data set and you're trying to fit. So I know this is SVM, but let's pretend we're talking about perceptrons. Well, let's pretend we're dealing with a perceptron here. And imagine you're trying to fit a perceptron here using the perceptron learning rule. Now you can imagine that there is no way to cut this data set such that all the blue guys are on one side and all the red guys on the other. In other words, your weights are going to always shift. You'll always be bumping and nudging your weights, right? You're not going to converge according to the perceptron learning rule. You're going to be infinitely nudging and bumping the weights because there's no way to find a line here which has no errors, right? So just something to remember about the the perceptron learning rule is that it will only converge, it will only work properly for your perfectly linearly separable data. Something to keep in mind. Now here's something a little different. It's the gradient descent applied to your perceptron learning. Now, hopefully we're all kind of familiar with gradient descent. The idea behind gradient descent is we have a little diagram here. So the idea behind gradient descent is, let's assume this here surface is our some sort of cost function, say sum square error. Let's just say this is sum square error, and error is something we want to minimize. We want to minimize our cost function, our sum square error. Now these are two weights. You can imagine, let's pretend we're doing some sort of linear regression. So we've got our W0, which is our intercept term, and our W1, which is our gradient term, because this is it's only got two terms. It's our straight line regression. Now it's an optimization problem. We want to find the best weights, the W's, that will give us the lowest sum square error. So the way you go about doing this is, you initialize the weights as something random. So this has been initialized, say here, to W0 is, I don't know, say 1.5, and then W1 is, I don't know, say 2.5. So say 1.5, 2.5. Now what you do is you calculate the gradient vector, right? And the gradient vector's the gradient vector will be tangential to the I guess this surface. And then what you want to do is, actually the gradient vector should be pointing the other way. This is the negative gradient vector, right? So if you're trying to minimize something, you want to go in the direction opposite to the gradient vector, right? Because the gradient points up, right? It points to so the gradient will be pointing up towards where the slope is increasing, right? So if it's a cost function, we want to decrease, which is why we go negative. We go negative the gradient vector. So this is negative the gradient vector, and it's telling us to move in this direction. Oh, sorry, maybe to move in this direction, right? So we increment, we nudge the weight vector W0 and W1. We move it that way, and then we do the same thing. And if you calculate the gradient vector, it'll tell us to keep going down, 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 and eventually we'll end up down there at the global minimum, and that will be minimizing the sum square error in this case. So that's the concept, high level concept of your gradient descent. Now we can apply this to your perceptron learning as well. So okay, so you can view it one of two ways. You can view it weight by weight. So this could be, say, W0, or this could be W1, and with each weight, you nudge it by negative I guess the gradient, right? And so just something to recall here is, so the gradient vector points towards the direction of increasing slope. Let's move over here. If we want to minimize, we want to go in the opposite direction. Hence, we take the negative gradient / derivative. If it's one dimensional here, so we've got the partial, so not the gradient vector. Okay, so hopefully we understand why we do this. So for each of our W's, for each of our weights, we will move in opposite the direction of the gradient, or the component of the gradient vector, or the derivative, or the partial derivative, right? You can also do it all at once. So if you did it this way, you have a for loop, and you'd loop across each of the components, or you can do the whole thing, the whole guy at once. So you have your weight vector, and you update the weight. You can see it's the same thing, isn't it? The only difference is you've lost the index. So now you're doing everything at once, and this is this is called our gradient vector. So the gradient vector is essentially this guy here. So this gradient vector, or this upside down triangle, or this what's it called, nabla, is it's just a vector with all your partials with respect to that function. So this is a vector with all your partials for each of your arguments within this function, and it's all with respect to this guy, but you're differentiating the j. That's the function you are calculating your partials on. So if you can see, you can do it one of two ways. You can do it all at once. Sorry, here you can do it all at once. We can step through and do it one by one. Okay. Now, of course, no matter which way you look at it, right? How you change your weight vector really depends on J. So J could be a bunch of things. So it could be a variety of different cost functions, but we'll be looking at the sum square error, which is a bit easier to deal with, and it's something we should be somewhat familiar with, is what we will be looking at in the slides here. I believe in the lecture slides, they look at the gradient descent on your sigmoid function, and if not in the lecture slides, they look at gradient descent performed on this here, the sigmoid. This in the Jupyter notebook they definitely cover it. I don't know if it's here. There's back propagation. Gradient descent. Yeah, cool. Yep, gradient descent. So you can look at gradient descent a variety of different ways, but remember you are differentiating a function, some sort of cost function. So you could look at, say, the sum square error, or you could look at, say, the sigmoid. It really depends on what you're differentiating, what function you're differentiating. Okay. Now, something interesting is if your cost function is your sum square error, then this is the same as the Perceptron learning rule. I mean, I won't go through the maths, but what you can do is you can just set this up, and then you just differentiate a couple of times, and you'll see that, oh, actually, so this is the update rule for gradient descent using sum square error. Now, this maybe I'll compare it side by side so you can kind of see this Perceptron learning rule. Here we go. So now why are these two the same? So this steps so this here looks at the difference between your estimator and your your target, and if these are the same, it means that you didn't misclassify. You did a good job, right? It was correct. So this update rule, so this derivative, it's only non-zero if there's a misclassification. That's like this, isn't it? This only kicks in when there's a misclassification. So when there's a misclassification, in other words, your predicted and the actual are different, then this actually kicks in. Now, what is this? When your predicted and actual are different, let's say it's I don't know, you predicted 1, but it's actually so let's say you predicted -1, but it's actually meant to be 1. Then this ends up being -1 or -1. So it's just -2, right? So it's -2 times your x, which should look familiar here, isn't it? You're bumping it up by the feature value here, right? I mean, the only difference is, okay, fine, this is 2 and that's 1, but really you could just scale it in your eta, right? If you set this eta here to half of that eta, then it's the same. But hopefully you can see, that's equivalent, right? If the cost function is your sum square error. Now, the other cool thing about this sum square error, this gradient descent with sum square error, is that it's guaranteed to succeed. And I think there's another slide. Here we go. Yeah. So the difference between the two rules, the two ways of learning. So your Perceptron learning rule only works if it's perfectly linearly separable, and you need a sufficiently small learning rate, because you might jump over the a global minima. Now with gradient descent, it's always guaranteed to work. Again, you need a sufficiently small learning rate, because otherwise, if it's too big, you could just jump left, right, left, right, left, right. You'll never land at the minimum. Obviously, you might have some sort of tolerance that, if it's close enough, it's good enough. It could be some sort of, I don't know, like tolerance for like floating point error or something. I'm not sure, something small, right? Now, why is this guaranteed to converge? So if you actually go around, and I actually bothered to do this last night, but if you differentiate this, if you take the cost function minimization problem, right, and then you differentiate it a second time, you'll find that it is always positive, right? I think if you differentiate one of these guys. But if you do a bit of calculus, you'll find that this cost function is it's concave up. You know, it's the second derivative is positive everywhere, right? So it's a convex optimization problem. So you're not going to be stuck in some local minimum. You'll definitely get down to the bottom, assuming your learning rate is low enough. Okay. So the other thing I want to talk about is your gradient descent. There's a bunch of different types. You have your I think you can go through this mass, but I think it's a little simpler over here. The way I want you to think about it is your batch gradient descent only updates after you've gone through the whole data set, whereas your incremental updates at each data point. So for your batch, you'll calculate the gradient using the entire data set, and then you'll update the weights. Now incremental, you'll calculate it using one data point, and then you'll update the weights, all right? So your batch, you go through the entire data set, and then you update the weights based on that entire data set, and then you repeat. Your incremental, you go through one by one by one by one. So I mean, your batch gradient descent is a more, I guess, perfect or accurate way to go about doing it. But it is costly because you have to step through the entire data set. In practice, they like using incremental gradient descent a bit more because, I mean, yeah, you lose a bit of accuracy, but it's just so much faster. It can often converge a lot quicker as well. So the difference between your stochastic and incremental gradient descent is your stochastic gradient descent. It is your incremental gradient descent, but you just choose your points at random. Okay, so. I don't know if you've ever seen the picture of where they show you the difference between your batch and your batch. There's a picture lying around somewhere. I'm sure I can find it. But you can kind of think of it, your batch descent is actually maybe something like this. Yeah, this guy here. Right, so ignore mini batch, that's something else. Just look at the purple and the blue. So you can think of your batch gradient descent as, you go through your batch gradient descent as, think about someone trying to, and I'm stealing this analogy off somewhere, I don't know where I picked it up, but I think it's a good one. Gradient descent, you imagine you're a man, a person trying to go down a hill, right? Trying to find the valleys. You get into the bottom valley. Now your batch gradient descent is analogous to you stop, you look around, and you look at all your data, and you take one slow, steady, accurate step at the point in the direction which is the steepest downwards, right? So every step is it's good. It's a really good calculated step. It's a direction which is the steepest descent, but it's slower because you're sitting there, you're pausing, you're looking at all your data. You're trying to work, okay, which is the best, which is the steepest descent. Now, your stochastic gradient descent, you can kind of think of it as, and again, I'm stealing this analogy from someone, I don't know who, as a drunk person just taking many steps, many quick steps, but it's sort of drifting down towards the bottom of the hill. Now, the part where the analogy breaks down is, I can't imagine the drunk person, unless he falls over and rolls down, maybe that's why it's faster. But, often the drunk person isn't as good as a lot of things, but, that's where the analogy breaks down here, right? So your stochastic gradient descent, drunk person just taking really quick steps and not calculated. Your batch gradient descent, you're stopping, you're looking at all your data, and you're taking a slow, calculated step. In practice, the drunk guy wins. And you can see, that's the other thing. You can see as well, the drunk guy doesn't end up necessarily at the global minimum, but it's good enough, and it's a lot faster to converge, or get to a point where it's close enough to convergence. Cool. Now let's jump back to the Jupyter notebook, because I'm running short on time again. So the second part that they go through in the Jupyter notebook is they implement gradient descent. So the first part was your perceptron learning rule. Now it's your gradient descent. Now they do gradient descent on using a sigmoid function. So it wasn't just the the sum square error, which is what I was talking about before. So let's see what's happening here. Right. This was the sine function that we saw before. But now we're using a sigmoid function. So let me pull up the sigmoid function so you guys all kind of feel of what it looks like in the back of your head. But essentially it's constrained. The range is 0 to 1, and the domain is all real numbers. And it's useful in a whole bunch of places. It's you can imagine it's useful for generating probability. Let's say output is the real number line, but probabilities have to be between 0 and 1. So you sigmoid squishification function. So there's an excellent YouTube channel which I highly recommend. You might have heard of it. It's a guy called Where is he? Yeah, 3 blue 1 brown, and he calls the sigmoid function the sigmoid squishification function. It was either him or Khan Academy. I can't remember who. Either way, one way to think about your sigmoid function is it squishes the real number line into something between 0 and 1, which is perfect for probability. Okay, this is a sigmoid function. Back to our Jupyter notebook. That's a sigmoid function here, and if you use a bit of calculus, you'll find that if you differentiate, it looks something like this. And yeah, so this is a sigmoid function again with different parameters. And look, either way, you can see that it's a domain is a real number line, and it's between 0 and 1. Okay. Oh, sorry. So look, I should probably say the. Okay, it means some errors. Sorry. I think I might have said a few things which might have been technically correct. So we are still minimizing the sum of square areas here, but the activation function is your sigmoid, which will change your optimization problem. Now, in the examples we're looking at before, they were using the sine function, right, as the activation function before it gets to the output layer, right? So maybe I'll say that again, just to clarify what I'm saying in case I've said the wrong thing. But in our examples so far in the slides, we considered a case where the output layer we use a sine function, so it's either +1 or -1, right? And we use a sine function for the output layer, but we are also trying to minimize the sum square error. Now in this example here, instead of using a sine function, we are using a sigmoid function, which is this shape here. But we are also trying to minimize the sum square error or the mean square error, which is equivalent. Okay, just to clarify. Okay. Right, so here's what we're trying to minimize, and then you can go through the calculus in your own time, but you can set up the gradient vector as something like this, right? And each one of these components, and they've used L for the loss function. I'm using them loosely interchangeably, your cost function, your loss function. I think there's a technical difference between the two, but I think they're used relatively interchangeably in the course. It could be that. Yeah, I can't remember which one's which. One was at the record level, the observation level. One was for the whole data set. But again, I've seen it used interchangeably within this course. But this L here, it's not a likelihood function. It's the loss function, which again in this course can be used interchangeably with your cost function. It's something you want to minimize. Okay. So in your gradient vector, so it's a gradient vector. So all the partial derivatives of this loss function or cost function with respect to your weight vector. So each component is each element, the derivative with respect to each element of your weight vector. And this derivative was this chap here. Okay, so if you sub it in, that's what you get. So that's essentially what they're coding up here. Right, your loss function for each individual observation. It's your target minus your predicted value. So what's happening here? This is our, I guess, our sum product of our weights and features or inputs. So this was that capital sigma that I was using in the slides. That's what that guy is. Now this is a sigmoid function, isn't it? Okay, so then they apply the sigmoid activation function to the activation, or the capital sigma, which is how I've denoted it in my slides. Cool. And they're squaring it. Because well, we're dealing with it to get the SSE/MSE, or the sum square error, or the mean square error. Okay. Now the gradient loss should be yeah, it looks like this guy here, isn't it? Yeah. So it's where you we were trying to generate this here, the gradient, so we know in which way to step. Okay, so this tells us the direction or the opposite of the direction to step. Again, because we're minimizing, we want to go in the direction that's opposite the gradient vector. Okay, and here's where we perform our gradient descent. So T is the number of updates. That's how many updates, how many iterations. So for each of the iterations, you step through the entire data set and you update the gradient vector. Okay, and so you step through each row of the data sets, and then you increment. I guess you update the gradient vector. Okay. And then here's where we update our weight vector by bumping it in the opposite direction of the gradient, because we are minimizing. Okay, let me just move that over here. Cool. So this is our gradient descent, and nope. Ah, shoot. Let's go back. Can we go back? Yeah, cool. And this is it in action. We can see here it's been initialized some random weights, and then it'll calculate the gradient, and this is the gradient. So the gradient is tangential this line. So we need to go in the opposite direction. We want to move it that way. Okay. Oh, sorry. We need to bump the weights that way, right? So we'll bump the weights by. Actually, sorry. We need to bump. We take this gradient vector, and we multiply it with our target and our features and our inputs, and that tells us how to bump the weight. So we bump the weights, okay, and then we keep bumping the weights until we've converged. So here, notice how it's not perfectly linearly separable. There's two errors. There's an error here. There's an error here. There's an incorrectly classified point here. But it's okay, because the loss. We keep stepping through, and the loss, doesn't. Actually, sorry, I haven't converged yet. Go down here. Okay, we've converged. Okay, so we've converged here at this point, right? Okay, and we know we have converged when. Where's this number of observations? Where is our convergence flag? Okay, I don't think there's a convergence flag or indicator here. I could be wrong. Looks like they're just stepping through and seeing how it goes. But you could have something there that looks at the change in error to see or the change in weight to see if there's any movement, to see if it's sort of settled down. It's not here, but you can add it to this implementation, and then you can do a few random restarts and take the one which has the best error. Okay, now the last one they implement is your stochastic gradient descent. So recall the difference between all these guys. So your stochastic gradient descent, where are you? Here. Okay, so we're going through each of these points at random. It's incremental, so we go through each data point and then update the weight vector, rather than batch, where we go through the entire data set and then update the weights. Okay, now stochastic gradient descent, it is incremental, but we choose the points that are at random. So this is what this last implementation here is. Let's have a look. Right, so T is just a number of iterations, and Where's the randomness? Gradient loss. Now this is something I have to try and work out, but I've seen in some places stochastic gradient descent has to be random, and other places it doesn't have to be random. Now I was under the impression it could be, well, had to be random, but at least in this implementation, I could be wrong, but I don't really see any randomness. You go through and you step through each of them. Yeah, I don't really see any randomness here. Although to be fair, I have seen incremental gradient descent referred to as stochastic once or twice. Let's go to source of truth, Wikipedia. I'm not sure what the lecture slides say actually. Now, is it random or not? Could be wrong. So here we go. Yeah, so here it says it's random, at least according to Wikipedia. There you go, it's random. Okay. Now, someone correct me if I'm wrong, but I don't see any random shuffling necessarily. I don't see any randomness being introduced. Anyways, I think I've seen it in places where it's not random. So let's just look in the lecture slides. Okay, so I guess in the lecture slides it's used interchangeably. So maybe I'll make that point here. Okay, according to Wiki, but it's in the lecture slides they're used interchangeably. Now I've also seen them used interchangeably here and there, so I mean I'm not really sure if there's a clear consensus as to which way it should be, but again, at least within this course, the lecture slides are the source of truth, so I'll go with this here where they're used interchangeably, so something to keep in mind. Okay. Now, I think that's all there is in terms of this here, the Jupyter Notebook. Let me quickly step through the rest of my slides. Right, and then the development on top of the Perceptron is your neural network, okay? So let's start by looking at this guy here, which is the simpler, I mean, this is a really simple neural network. So with your Perceptron, right, essentially you don't have the hidden layer, okay? There was no hidden layer. So the Perceptron just had the input layer and then some activation function and then straight to the output layer. Now your neural network, it's called a network because you have these networks of neurons, is when you have at least when there's at least one hidden layer. Okay, so a neural network has at least one hidden layer. Okay, so what do these layers do? It adds an extra layer of complexity and allows you to complexity and flexibility, and allows you to model much more things. It adds a lot more power and flexibility to the model, right? Now with your Perceptron can only really work well with perfectly linearly, well, I guess with linear data. But with artificial neural networks, you can handle non-linear data, right? It doesn't have to be. Now, when I say linear data, I mean this is linear because you can perfectly cut it in half. But there can be weird and odd and wonderful sort of shapes. Now, by adding this hidden layer, you can handle a level of non-linearity in the data. I think there's another caveat to this. It might be something with activation functions. But the artificial neural network definitely can handle your non-linear data. It's a lot more flexible, a lot more powerful. So let's see what's happening here, right? You added this guy here, and each one of these is a neuron. Actually, you can consider each of these to be a neuron, right? I mean, this could be the input neuron, and these are neurons. This is the output neuron. You can think of it however you want, but I guess at least these are the perceptrons. So you have your input layer, and now instead of having just straight to the output, you have another bunch of neurons here, another bunch of perceptrons here, and each of these have their own weights and inputs and outputs, right? So maybe I'll get a picture of a Perceptron next to it, so it's a bit easier to see. I'll get this guy, right? Oh, okay, well, it's right there, isn't it? Sorry, didn't see that. Okay, so this is your original guy here, right? So you can imagine if you were just to look at, you know, just this section. It's a good way to do this. If you were just to, okay, well, you can see. If you just look at this section here and assume this is output layer, that would just be a perceptron. Now, out of these other guys here, and the important thing to note is that each of these, the term here is fully connected. And fully connected here just means that you know, every layer is connected, has a line, has a connection, has a weight to everything in the previous layer, right? So you can see here this neuron here is connected to boom, 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 boom. And this neuron here is connected to everything in the previous layer, and the same can be said of this guy here is connected to everything in the previous layer. So it's fully connected. So hopefully you can see how, you know, the number of weights has gone up a lot, right? There's a lot more parameters, a lot more weights, there's a lot more flexibility. You can model a lot more, you can a lot more complicated data, right? So this is your perceptron, and you've expanded it by having more perceptrons, right? You have this guy here, and then there's another layer here, and then these will all have weights, and then there'll be an activation function here, right? So these all have activation functions, right? These, if you look at this neuron here, it takes in inputs from x1 to x5, each has its own weight, and then this will have an activation function. And if the activation function is activated, then it'll send something along here, and this will have its own activation function. So each one of these guys has an activation function, as well as a weight, right? So each one of those red lines represents a weight, okay? And here, you know, they'll all feed in, and, you know, we'll go this way, and you hopefully can appreciate how, you know, it's a whole network, it's a whole bunch of these guys. And the complexity of the model has increased quite a bit because, well, look at the number of red lines. You know, say, you know, if you got rid of these guys and these guys and these guys, if it were indeed just, you know, what I've circled here, the number of weights is just, what is that? Just, it's 5 weights, isn't it? Now, this very simple neural network, it's gone from 5 weights to 15 plus 3, 18 weights, 5 weights to 18 weights. There's a lot more parameters, a lot more flexibility in the model, right? You can capture a lot more, you can model more sophisticated relationships, right? Okay. So I might be a bit convoluted, but hopefully you get a bit of a flavor of what this neural network is, okay? And this here's another picture. And this one is a simpler one because it has one hidden layer. This is 2 hidden layers, right? And you know, the number of, you know, weights you can see is, you know, is far greater, right? So it's what is this? 5 times 4. So there's 20 weights here plus 2, 4, 6, 7 times 2, 4, 5, 35 plus another 35 weights plus 3 times 2, 4, 6, 7 plus 21 weights. That's a lot more weights than over here, right? And then in this case you have 3 output layers. And why do you have 3 output layers? You can have, it depends on what you're trying to do, you know. This could be, you know, some sort of classification. Each one of these could be, you know, a color. Maybe you're trying to, or maybe a type of fish. There's 3 types of fish, you know, and you know, and these are different features. I'm trying to classify fish, and it goes through here. And you know, if this one's activated, then maybe it's salmon. If this one, maybe it's, I don't know, tuna. If this one, maybe it's sea bass. It could be a whole variety of different things. But you know, it doesn't have to just be one guy at the end, right? Of course, you can still have classification even if there is just one output. What you do is, you know, let's say this goes to the output layer, and then you could just chuck a sign function onto here, and then it'll be 2 things, right? So you can use a variety of different ways. Okay, activation function. So I've been talking about this a bit. So the activation. So why is it even called an activation function? Let's take a step back here, right? Now, in your brain, okay, right, and hopefully you're starting to see that the link between your artificial, you know, neuron and your biological neuron. Now there's a bunch of, now you can think of the all these guys here. You can, on the outside, you can think of these connections. You can think of these as the input layer. So input layer here. And then you have the weights, which are the strengths of the neural connections. Again, I'm probably bastardizing this the medical terminology here, but bear with me. So you have your input layer, which is fed in from all the other neurons that this neuron is wired up to, and your activation essentially is your activation function. Why is it called that? If there's enough of an electrical impulse from all these guys feeding into here, then this will spark. Then this will spark and feed electrical impulse to the other neurons that it's connected to. That's why it's called activation function, whether the neuron is active or not. Cool. So there's a variety of different ways you can set the activation function. We've seen the binary. We've seen the step function. I mean, the one we've looked at is +1, -1, but you can define it to whatever you like. This one here is 0, 1. There's identity, which is just it's just itself. And you've seen the logistic function. There's a whole bunch of different ones. Other common ones are your ReLU and leaky ReLU functions, and they all have a variety of different uses. Now, so these things can actually form hyperparameters that you'll tune. So things that you're learning, right? Your things like optimization function. So let me show you something. Now in practice, actually maybe I'm jumping in. So sorry, maybe I'll leave this till the end. Where is it? Okay. Now the next thing we'll talk about is backpropagation. Okay. So I think hopefully we're all reasonably comfortable with how we learn with the perceptron with just say one neuron. We either use the perceptron learning, or better yet, we use gradient descent, right? Now, when you have a neural network such as this, right? Oh, and there's a lot of things to consider, and there's so many moving parts. Now, the way backpropagation works is, I'll lead you to go through the details in your own time. Is they'll start at the end, they'll start at the output layer, right? And they'll look at all the misclassifications. Okay, cool. These guys have been misclassified, and they'll say, okay, right, if we wanted to fix this up, what bumps and nudges will we need to the previous layer to fix it up? And then they'll pass it along. They'll do a backwards pass. Okay. And then they'll go here. And then they'll go, okay, what was wrong here? Okay. And they'll pass it along, and they'll pass it along, right? So at a high level, they'll look at all the misclassified examples, and they will go back and work out what bumps and nudges would have been needed to actually get to the correct to get to a better set of weights, right? Okay, so for you step through each of the training examples, for each, so you start at the output units, you start at the end, okay, and then you work out what nudges, what bumps you would have needed to actually get to the correct answer. And then you do the same thing for each of the hidden units. You do it here, you do it here, and then you update the weight vectors, and you nudge everything, and then you repeat and you repeat and you repeat. Okay. Now, something I highly recommend is this video. I think it explains backpropagation in a very, perhaps the clearest way I've seen. And animations are fantastic. You might have heard of this guy. This person here. Fantastic videos. I've got some good ones on neural networks as well. He'll do a far better job of explaining this than I can. I try my best, but I can't beat him. He's fantastic, right? I highly recommend his channel. So if you want an animated animation of how your backpropagation works, I'd recommend this video. Now, I am running very short on time, and the Jupyter notebooks didn't talk too much about your CNNs, but real quickly. Your convolutional neural networks, so it's another type of your neural networks. These have been optimized. So these are really for image data. And one of the problems with your normal neural networks is the number of weights you have to optimize just blows up, and it just becomes just unfathomably hard to optimize. And the reason being, you think about how many pixels you have. Let's say a small photo, let's say 1,000 by 1,000 pixels. Let's say it's square, so you have a million. That's already a million inputs, right? And then you might have 3 RGB channels. You have 3 channels for your RGB. That's 3 million weights just for 1,000 by 1,000 picture, which isn't even that big in the grand scheme of things, right? And then if you have all these hidden layers, it just blows up. Now your CNN does a couple of interesting things to sort of minimize the number of weights, and it's got a bunch of cool things which I guess, emulate what Mother Nature does. When they're when they're looking at stuff. So your regular multi-layer perceptron, or your regular artificial neural network, it was fully connected. So everything, by fully connected, I mean everything in one layer is connected to the previous layer, right? Now this blows up the number of weights you need. Now in your CNN, it's locally connected until you get to the end. Now what do I mean by locally connected? Now let's look at this diagram here. So each one of these is a hidden layer. Now the other thing as well is that notice how it's arranged in a 3D array, but I'll talk about that in a moment. But let's just pretend that this hidden layer is kind of the same as this. Now this layer here, this input layer, is only wired up to this section of the next hidden layer, which in turn is only wired up to this section of this next hidden layer. So you can see here how, you can imagine, right? Because this square only has to wire up to this square instead of having to wire up to everything here, it really, really, really minimizes the number of weights you need. And, then this effect is blown up, several fold, because each one of these is only locally connected. It's only at the end where you have another fully connected normal neural network to clean things up at the end, to perform your classification task, whatever it may be. But in these ones here, you save a lot of computing power that you need. And the other thing as well, it's arranged in a 3D array, so which kind of makes sense when we're thinking about images, right? You have your your 2D image, and then there's 3 channels for RGB, so that's the input layer, right? There's a couple of different things as well. There's filters. So these little guys, they'll slide along here. You can imagine this guy. You can imagine with the input layer, and then this filter here, it slides across. You can think of it sliding across input layer, and it will connect up to the next layer. And there's a bunch of different filters you can apply, like things like edge detection filters, which mimic what we do in real life, which really helps this network learn about this image data. Okay, I'm gonna wrap up here. It's been 1.5 hours almost, but I'd like to conclude with a few things. So I'd really appreciate it if you feel like this is my experience survey. I've been encouraged by the faculty to follow this long. So if you could, I'd really appreciate that. Thank you very much. Thank you. If you are more curious about your neural networks, there's a few things I'd recommend. The first starting point would be scikit-learn has a multi-layer perceptron. It's not the best in the sense that it's not really flexible. It's not really that powerful, but it does live in the sklearn universe, and I think we're all familiar with the sklearn API now because of all the homework, which I presume a lot of you guys have done in scikit-learn and Python. So that's one advantage. Now, once you're bored of that, I think another good point, another good place to look at is Keras. Now, there's a bunch of good deep neural network libraries, deep learning libraries, such as TensorFlow, PyTorch, etc. But to my knowledge, Keras is one of the easier to use ones. And so unless you're getting into the weapons and really intense stuff, which I suspect that if you were, you might not be doing this course. Then I think Keras is a good place to look at after that. And here's a bit of a screenshot as to how it looks, and you can see it's quite easy. You have your data, and you have your multi-layer perceptron. It could be a classifier, or regressor. This is just the descent method, the optimization method, and a bunch of hyperparameters you can tune. Hidden layers, and just a random seed, random state. So in just a couple of lines, you can fit a neural network. Now, obviously, this isn't going to perform well, and as I say, in sklearn, it's not optimized in the best manner, and it's not as powerful, as flexible as other things. But it's a good starting point. And in terms of image recognition, there's a bunch of libraries sitting around that have pre-trained networks you can use and just sort of tweak with, which are quite good. I think OpenCV is a popular one. So if not, if you are interested as well, there's COMP9417, which goes into this in more detail. Cool. So I'll wrap up here. So thank you all for your time. So please fill this out. I'd really appreciate it. Thank you very much. And everything has been uploaded, and I'll upload this recording to YouTube later. Have a good weekend, guys. Stay home, stay safe, and have a good weekend. Bye.